What specific problem does your method aim to solve in the context of large language models, particularly regarding reasoning tasks and compute allocation?
Our method aims to address the limitations of existing approaches in large language models, LLMs, that generate discrete intermediate outputs, which complicates end-to-end training and restricts adaptive compute allocation during reasoning tasks. Specifically, we introduce a coprocessor that augments the LLM's key value, KV cache, with context-dependent latent embeddings, allowing the model to leverage enhanced internal representations without modifying its architecture. This approach facilitates end-to-end differentiability and enables asynchronous operation, allowing the LLM to bank computation by refining its memory independently of generating responses. Our experiments demonstrate that this augmentation significantly improves performance on reasoning-intensive tasks, such as GSM-8K and MMLU, by enabling the model to perform more extensive thinking in the latent space. Ultimately, our method enhances the LLM's reasoning capabilities while optimizing compute allocation within a fixed budget.
How does the proposed method work? Illustrate it step by step, detailing the role of the coprocessor and the process of KV cache augmentation.
The proposed method enhances a frozen large language model, LLM, by introducing a coprocessor that operates on the key value, KV cache, generated by the LLM. The process unfolds in three main stages. 1. KV cache generation. The input sequence, X, is processed by the frozen LLM to create its KV cache, which contains internal representations of the input while keeping the LLM's weights unchanged. 2. Augmentation. The KV cache is then passed to the coprocessor, which shares the same architecture as the LLM. The coprocessor receives additional soft tokens, abstract prompts, and generates a sequence of latent embeddings, Z, based on the KV cache and these tokens. This step allows the coprocessor to produce context-dependent embeddings that enhance the information available for subsequent processing. 3. LLM generation with augmented context. The generated latent embeddings, Z, are appended to the original KV cache, creating an enriched cache. This augmented cache is fed back into the frozen LLM, which then generates the output sequence, Y, using both the original input, X, and the coprocessor's output, Z. This method allows the LLM to leverage the coprocessor's latent inferences without requiring it to verbalize intermediate steps, thus improving reasoning capabilities and overall performance on reasoning-intensive tasks.
Can you provide a simple yet illustrative example that demonstrates the inner workings of your algorithm, specifically how the coprocessor generates latent embeddings based on an input sequence?
To illustrate the inner workings of our algorithm, consider an input sequence ABCDEF. During processing, the frozen LLM generates a key value, KV cache, from this input. The coprocessor then takes this KV cache and a set of distinct soft tokens, which serve as abstract prompts, to produce latent embeddings. For instance, if the coprocessor is tasked with augmenting the input at the positions of B and D, it generates latent embeddings, E, G, B and B for B, and D for D. These embeddings are then appended to the original KV cache, enriching the context that the LLM uses to predict subsequent tokens, such as C and D after B, and E and F after D. This process allows the LLM to leverage the coprocessor's latent inferences without explicitly verbalizing intermediate steps, enhancing its reasoning capabilities.
What are the theoretical and practical benefits of using your method compared to existing approaches like the pause token and zero-shot chain of thought prompting?
The theoretical benefits of our method, which utilizes a coprocessor to generate context-dependent latent embeddings, include enhanced reasoning capabilities through dynamic input-specific representations, as opposed to the fixed embeddings used in the pause token method. This allows for a more tailored approach to augmenting the KV cache, leading to improved performance on reasoning tasks. Practically, our method demonstrates superior performance metrics, achieving a perplexity of 10/60 and an accuracy of 26.76% on the GSM-8K dataset, compared to 11.63 and 22.37% for the pause token, respectively. Additionally, our approach generates latent embeddings in a single forward pass, making it more efficient than zero-shot chain-of-thought prompting, which requires sequential token generation. Overall, our method not only improves reasoning performance, but also enhances computational efficiency, making it a more effective solution for augmenting LLMs.
How did you validate or test the effectiveness of your method? Discuss the experimental design, metrics used, and the datasets evaluated.
We validated our method using the frozen Gemma 2-2B model, training it on a diverse dataset mixture comprising 2 trillion tokens, which included web documents, code, and scientific articles. The experimental design involved training the coprocessor while keeping the LLM frozen, with a batch size of 1024 and 100,000 training steps, utilizing 128 randomly sampled augmentation positions and predicting 16 ahead tokens. We evaluated the effectiveness of our approach through perplexity metrics on a proprietary validation dataset, measuring the model's ability to predict future tokens, and by assessing performance on public benchmarks such as GSM-8K, MMLU, and others. The metrics used included perplexity for next token prediction and accuracy for reasoning tasks, with results indicating significant improvements in both metrics as the number of latent embeddings increased. For instance, we observed a 10.05% accuracy improvement on GSM-8K when augmenting the model with 64 latent embeddings, demonstrating the effectiveness of our cache augmentation approach.
What specific results did you achieve with your method, including any performance improvements over baseline models on reasoning tasks, and how do these results highlight the significance of your approach?
Our method demonstrated significant performance improvements over the baseline frozen Gemma 2-2B model on various reasoning tasks. For instance, we achieved a 10.05% accuracy increase on the GSM-8K dataset and a 70% improvement on the MMLU benchmark when augmenting the model with 64 latent embeddings. Additionally, our approach consistently reduced perplexity across multiple tokens, indicating enhanced prediction capabilities, even extending beyond the training parameters. The results show a strong correlation between the number of latent embeddings and performance gains, underscoring the effectiveness of our coprocessor in facilitating deeper reasoning. Overall, these findings highlight the potential of our KV cache augmentation method to significantly enhance the reasoning capabilities of large language models without requiring task-specific training.